In this paper, we built a high-quality event flow dataset and proposed an adaptive density module. Existing methods of event flow dataset creation can be classified into two types. First, directly capturing from real event cameras and getting depth information from lidar sensors. Second, moving foregrounds on top of a background image to create synthesized flow motions and apply frame interpolation to create events. However, both types of datasets present challenges that make training the event flow network difficult. The captured dataset from real event camera have difficulty in obtaining dense optical flow labels. The flow labels can be calculated accurately when the depth values of lidar scans are available. However, lidar scans are sparse, and so do the flow labels. Furthermore, the density of captured events data varies greatly among different datasets due to the use of different camera models. Existing synthetic datasets use frame interpolation to generate events. However, occlusion issues can lead to incorrect interpolated frames and produce inaccurate events. Additionally, the simple motions for foreground objects in synthetic datasets leads to unrealistic optical flow labels. In order to create a realistic event dataset for optical flow learning, we propose to employ a graphics engine with 3D scenes for data generation. Given 3D scenes, we first define camera trajectories. Then we render high frame rate videos based on the motion magnitude of the optical flow labels. Finally, we generate event streams by rendering high frame rate videos and simulating the event trigger mechanism using the event simulator. We propose a multi-density rendered event optical flow dataset called as MDR dataset. Our MDR dataset consists of 80,000 training samples and 6,000 validation samples with accurate dense optical flow labels, including indoor and outdoor scenarios. The density distribution of event data in the training set ranges from 0.09 to 0.69. To demonstrate the effectiveness of our proposed MDR dataset, we train advanced optical flow networks on both MDR and MVSEC train sets using identical training settings. Then evaluate the trained networks on the MVSEC validation set. Results demonstrate that all networks trained on the MDR dataset outperform those trained on the MVSEC dataset. Our MDR dataset contains event data with various densities, so we can examine the impact of input event sequence density on optical flow learning. The experiments clearly show that the optical flow networks perform optimally when trained on event data with appropriate density. This emphasizes the crucial influence of event data density on the network's performance. We propose the ADM plugin to adjust the input density for different flow networks. It consists of two submodules, MDC and MDS. MDC globally adjusts the density of the input event representations from multi-scale features, and MDS picks the best pixel-wise density using selection weights via softmax operation. In order to verify the impact of our proposed ADM module, we conduct ablation experiments by plugging ADM into flow networks. Train these networks on both MDR dataset with the same setting except that ADM is enabled or not. Then test them on the MVSEC dataset. The results demonstrate that our ADM module can bring performance improvement for all supervised optical flow networks. We plug in ADM into KPAF flow to make ADM flow. Compare it with previous methods on the MVSEC evaluation set after trained on the MDR train set. Results show that our model trained on the MDR dataset achieves SOTA performance in both input settings of DT1 and DT4. Notably, our ADM flow demonstrates a 23.9% improvement for dense optical flow estimation in DT1 settings, reducing EPE from 0.67 to 0.51. Besides, our ADM flow also makes an 8% improvement in DT4 settings, reducing EPE from 1.75 to 1.61, surpassing previous methods. Our ADM flow achieves improved performance on other training datasets, highlighting the effectiveness and versatility of ADM. There are some qualitative results on the DUSEC test set. In conclusion, first, we propose a rendered event flow dataset MDR, created by Blender on indoor and outdoor scenes with accurate events and flow labels, covering a wide range of densities. Second, we propose an adaptive density module ADM, which is a plug-and-play module for handling varying event densities. Third, experiments show that MDR dataset can facilitate event flow learning, and various flow networks when equipped with ADM can further improve performances. Thank you very much.